Hi again, my name is Marcelo, and today I'm going to be doing Project Euler Problem 3. This one is quite straightforward, doesn't really have anything special or magic to it, just has a really large number and asks you to find the largest prime factor of that really large number. And it includes a smaller test case here for 13195. It lists the prime factors, and the answer for the largest prime factor would be 29. I'm going to be doing things a little bit different today. Instead of going for the most optimal solution, just going to go through a very general one using a reusable primes class. The idea is that a reusable primes class is useful for other project problems since a lot of them use prime numbers as well. So I'm going to start here creating a new Euler file using Python again. You can use whatever you want since these are just simple math problems. And to get started, let's go with creating a class of primes and creating a method called up2 and just initializing it to return an empty array because you want it to return a list of primes soon. So, and then we create a file which just imports the Euros file and it just gets the primes element, and let's just try it out with the value here, and this should just return as an empty array. Very nice. Let's try if10, then we should get a nice list of primes. So if you come here, what you're gonna do is you're gonna start with a prime sieve. So a prime sieve is just a list of booleans when you start with every boolean at 1. And if you find a number that multiplies to a certain index, you set the value in that index in that list to false to know that it's not a prime. So we start with a list of primes and we initialize everything to true. To make it inclusive, we multiply it through n plus 1 so that you know that n is included as well in case n is a prime. Then we're going to do a loop, but just place it as n here for now, and another loop where we want to loop through all of the elements in the range. And for now, let's just print I times j here so that it shows. And in the end, what you want to do is we want to list all of the indexes that are in that range if that value is still true by the end of the execution. So if it's considered a prime. So if you run here, we're just going to get a list of numbers below our target number. It's not that useful. We should actually just modify this to be n plus 1 as well. And we're going to start already by doing some efficiency optimization. So instead of going through all the numbers, we're just going to go through the odd one starting with 3. So we're just adding the steps here so that it actually checks both 3 and 2. And the idea here is that when we have these two numbers, we know that they are prime, and we just set it to false. But the way to check this is that if we go through every single one, this is going to cause an index a key error, so that it tries to access a place that is it's not. So what we're going to do actually, we're going to import from the mathlib. We import the value seal and square root, the methods, so that we only check the square root of n, and we add the plus 1 as kind of a cushion here. Same thing with the inner loop. So here we just do a division by the up value, so that now our upper bound is the complement to the division of n and I. And we're also just kind of going to go through the ceiling here, and we could add a safeguard here, but for now let's just not do this. And now that we're looping uh, through the odd numbers only, we just include a 2 here, and we kind of do the same loop here, that it should only find that it should only check for the odd numbers. So if we do this, we get 2, 3, 5, 7, and 9, but that 9 there, that's kind of wrong. So what did we do wrong here? One other thing we might do as well is just that if it's smaller than 2, we return an empty list because it shouldn't be checking the prime numbers. And what we might have done wrong here is that we might want to just loop through the square root of n plus 1 instead. And here we don't need a ceiling in this function, we just need to make sure that it goes all the way up. And yeah, so these are the 4 numbers which are prime below 10, so this looks like it works. Now we want that 5, because that 5 is a factor of 10, we don't really want the whole list. So let's just create a method called largest factor of n, and for now we return n because the number is a prime, then we get n as a response, so we just call largest factor and we get it here. But instead of, we're just going to get all of the primes up to that number, in this case here n. And since we only want the largest one, we just reverse the list and get the first one which matches the condition that, let's call this instead of I a p, because then it's a prime number, so we know that it's a prime factor, and if it's a prime, if the divides node is a factor, we know that it's the largest one. So I think this should work. It doesn't because we are using n here, so for 10 we're using 5, so this looks like it works. So if we went to 13195, it looks like it works as well. If we were to run this, it could actually crash because of the high value here. So we're gonna do something different instead. Is we don't really need the primes up to n, we just need the primes up to the square root of n. So if we were to just do here kind of the same thing we did in the other one, just get the ceiling of the square root, this should work as well. It's not going to be very optimal, but it gets the function fast enough. If we were to do something like just time it out and get a function here, yeah, so it's like under a second, and I'm not going to run through this project Euler now because again it's not optimized, so it's not going to pass other tests. But this was project Euler problem number 3. If you like this, subscribe. Let me know what you want to see. If you have any optimizations we could do here, I would love to just try and some problems as suggested by the audience. And thank you for watching.